But then the PCA by itself has several other applications. Okay, so since we are on it, right, I just thought in passing I'll also mention those. So the PCA, right, so one of the things is as a benchmark. Okay, so the KLT or PCA, whatever you want to call it, right, one of the things is it's a benchmark for let's say unitary transforms. Okay, serves as a benchmark for UTs, okay, which is unitary transform. But then a PCA also finds wide usage, okay, elsewhere. Okay, here probably, right, you simply limit it to being a benchmark, whereas places where it is used, for example, one is a dimensionality reduction. Even today, you will find people using PCA left and right, okay, for doing a dimensionality reduction. In fact, right, if you have read something about let's say autoencoders, especially the deep learning type, right? So when they actually build a deep learning autoencoder, which is typically non-linear, so the first thing they will show is that if you constrain, right, everything inside a deep network to be linear, then the kind of the encoder decoder structure that you get will be exactly similar to that of the PCA. It's in fact identical. You can show that what you end up doing there is in fact simply a PCA. Okay. So if you force the deep learning thing to be totally linear, okay, then it actually turns out that you will be implementing a PCA. Okay, and the dimensionality reduction by itself, right, people do for let's say various reasons, right? So for example, of course, this can all be lossy. That is okay, right? I mean, people are kind of willing to work with some say lossy, sort of a reduction. Because when you do this kind of a dimensional reduction, right, you may lose some information, but the idea is that you at least have an idea about how much you are losing and so on, and therefore you don't mind doing this kind of reduction. And there are kind of two ways. I mean, one is so the dimensionality kind of say reduction. One thing is to be able to go into a kind of a latent space, right, which is your feature space, where you say that I'm able to bring it down, so you can take some samples inside, and then you can think of having some kind of an encoder, right, which will actually take it down to a dimension which is much smaller. So in this case, right, think of let's say something like an n cross 1 vector going in, then you get something like an say m cross 1 where m is much less than n, and then of course then you send it through a decoder, right, and then you see outcomes and you see estimate of whatever is input. So right, you may not always get back this, but then the idea is that how much can you kind of go down by, so that right, you can actually minimize the error over let's say several examples, right? So these kind of things people always do, and here, which is where I said, I mean, if this was non-linear, then of course you can do much better than a PCA. But if you restrict all these guys to be linear, then what you will end up implementing is simply a PCA. On the other hand, right, people also do dimensionality reduction if you want to do some kind of this one, what do you call a visualization. Okay. What this means is that sometimes, right, you try to solve some kind of a classification problem, right? I mean, you may have n classes, right, and then you have whatever, right, it could be some features, right, that you have got for each class, but even these features can still be in some high dimensional space, right? Like for example, this m could still be in hundreds. So in a 100 dimensional space, how do I even see as to what is going on, right? Whether these groups are overlapping, whether these groups are actually separate, I mean, how well do they look, and so on. So in that space, right, you can't even imagine what is going on. So what they will do is they will finally bring it down to something like a 3 cross 1 sort of a vector, which means that you can actually plot it, right? And it's not for reconstruction purpose or anything, because nobody, right, typically will kind of bring it down all the way from 100 to a dimension of 3. But then this 3 or 2 is typically done, for example, right, sometimes people do a kind of 2 cross 1 in order to simply see as to where all those points. See, for example, right, if in that high dimensional space, if you think about, let's say, a person 1, right, his features are somewhere here, right, person 2's features are somewhere here, person 2's 3's features are somewhere here, we don't even know where they are, right? So therefore, if you do a PCA, bring down all the features, and then if you plot them, right, I mean, sometimes, even in the low dimensional space, you might be able to see that there is a good deal of separation going on, even though this will not reflect exactly what is going on there, because in that dimensional space, what may be separate may not be separate here. But then, right, many a time people use it simply to be able to show that that these classes are maybe, right, some overlap is there, but then, right, these are all kind of the intra-class variance is small, the inter-class variance is still reasonably large. So all that kind of this one is also done. So in fact, In fact, right, that is another place where they use it. Just bring it down. Just going to crash the whole this one dimension down to some like 2 or 3. But then that's not for reconstruction. That's simply to visualize, especially if you have features coming from say different classes, and you want to know how are they spaced out. One way to directly see could be like within as a 3x1 or a 2x1 kind of vector. Then people, the one application that, let's say, PCA, whenever somebody talks about PCA, is what is called eigenfaces. Right? This is something that used to be a very sort of a popular thing. Okay, it's no longer, because ever since deep learning networks came in and your deep face net and all came, right, then this PCA kind of faded into this one oblivion, especially for eigenfaces. But then this was one of the this was one of the algorithms this was one algorithm that was talked about a lot, right? During the days when, let's say, 85, 90 types. So at that time when, let's say, people started using PCA for doing face recognition. So again, the idea is like that. So if you are wondering, right, how they do this R computation, right? So what they will do is, so basically imagine that, right, you have lots of human faces. So you kind of stack all of them. Right, so for example, in this case, you can call this as some A. Okay, so here is a data matrix, right? So where you have, let's say, each vector is 4096. Let's say, suppose it's 64 cross 64, and suppose you have some by P, where P could be really large. Okay, so P will be much greater than 4096. Otherwise, right, you can't even learn anything. And the sort of a thumb rule is like, if M is the size of the data, then at least M square, but much more than that typically. Okay. So you need to have that many face images, for example, and also, right, it was not easy, because faces come in various sizes. Right, I may have your face that I could have taken once from close, maybe another face is from far, one is zoomed in, another is zoomed out. So what they would normally do is so they would scale. So they would do some kind of a normalization. So what this means is that for every face, right, they will make sure that the inter eye sort of a separation is a kind of a fixed number. So they will say something like, I don't know, it was about 20 pixels. Or something like that, right? So they will fix that number. So they'll take every face image, they'll make sure that the separation between the eye is that. So if it is already zoomed out, then it means that they will have to kind of blow it up. If it is zoomed in, then they'll have to shrink it a little bit so that right, because when you kind of slap, right, one above the other, you want all of them to be aligned, right? Otherwise, what will you learn? So all this, so it's not actually easy, right? So even today it is done, by the way, but except that right, deep networks seem to be much more robust to such changes and so on. But then even now, right, people actually do kind of create a data wherein at least these variations can be removed, right, so that what is really need to be learned can be learnt. Okay, so they will kind of do this normalization, and after normalization, right, you have all these phases stored up there. So you can think of this as so then what you will do is you will actually compute this covariance as simply AA transpose. You can even do it like that. Or you can actually take the other way, right? The usual way is like R hat, right, is equal to, what is that? So if you have P number of examples, right, so you'll say like 1 by P, then you go like I equal to 1 to P, and then let's say xi minus M transpose, where xi is right, xi is this, each sample is xi, this is like x1, this is like x2, and so on, right? So you can so the idea is that so the more examples you have here, the hope is that your estimate of R, right, is going to be good. Okay, this is R hat. Okay, this is how you typically get, whether you have phase or whether you have whatever else, right? If you have lots and lots of samples, you compute the mean of that, and then you do whatever right. You can then do this covariance thing, or you can also do directly from that data itself. And then once you have this R hat, then you will go through an eigenvalue, eigenvector kind of a decomposition. Typically SPD is used for that. We have not done SPD yet, but after this you use SPD to find the eigenvalues and eigenvectors for this. Then based on the eigenvalues, then you knock off whatever is not significant, then just use the significant eigenvectors, then you start. Now for example, right, in terms of face recognition, right, there, see again, what you wish to do later, right, will change. For example, right, if you want to do face recognition, okay, what you would do is, so imagine that, let's say, right, I have one person 1, a person 2, a person 3, right, something like whatever. Okay, what this means is that out of those 4,000, not out of those P P images, right, P number of images. Let's say that there are about n classes there. This is person 1, this is person 2, person 3. There are n number of them. N could be 1000 or something, right? It depends. But now people can do millions and all. Let's say keep it as a small number, right? You've got, let's say, right, 1000 individuals. Now you want to do a kind of a recognition. Now assume that for each people you have at least some examples. Okay, if you have one, then of course it's very hard to do anything. But assume that you have, let's say, 5 examples of each guy, suppose, okay, which is all right to assume. Okay, so let's say for each person you have about five examples. So what you would do is you will go back to that equation that we had, which is like V m cross 1. So where you had psi, which was m cross n, right, and then u minus m, right. So this m will be the average computed over all the p. Okay, so that is really independent of the person. So this m is independent of which individual you are kind of looking at. The m comes from the entire set, right. So the average of all the p examples is your m. Then right, what you would do is then for each person, right, what you will do is you will actually take his image number 1. Let's say if you're interested in computing, let's say, suppose I want to transform, we call it feature, right. Suppose I want to find the feature for, let's say, for this guy. Okay, suppose I call that V1. Okay, now V1 I want features for this guy. Then what I will do is the psi is again same for everybody. So the eigenfaces will be the same for all. So it's like m cross n, because you don't there's another way, but then that will require too many images for each person, which we can't afford to have. So the psi is computed over the entire set again. Okay, this is not really dependent on a person. So psi comes from the entire set of face images. Then let us say that you've got, like, for this person I've got let's say u11 minus m. Okay, m is again coming from the whole class. So u11 means right, image number 1 of this guy. Okay, and then you will do v2, which will involve u12, okay, and so on. And then let's say, right, I do this up to u15. Now what I can do is, what is typically done is, you take all these v1, v2, v3, v4, v5, which is with respect to the 5 images of this person that we have, you take the average, right, and then we can call this as, let's say, v1 or something. Okay, that will be the feature for this guy. Similarly, you go to the second guy, right, you get something like v2 for this person, v3, and so on. So we are like v1, v2, v3 for each person, right. So it's like it is the feature of this guy, which may be of a much lower dimension than the original image, because this m, right, depends upon how many eigenvectors you chose. So like I said, right, this can be as small as 100 dimensional. So this can be just a 100 dimensional vector or even 50 dimensional vector, and you take the average of all the features that you have got for that example, and now you store all of this, right. So for each person, right, because you have captured all this offline. For each person you have captured all these images. Well, ideally it can't be 5, because if I have just n as 1000, then there will only be 5000 images. Okay, so assume that, right, I've captured enough, or maybe the n is large enough, whatever. Okay, so that I get kind of, right, p. So this number of individuals times the number of images that I have should be equal to p, right. Now what you do is later, okay, now for example you have stored all of this with you, and then someone else comes in, right, one of these guys comes in with a new face now, then you actually find out this v for that guy. Again, what will you do? You'll use the same psi, and then you will be this new image, sort of a test image that has come in, and then m is still the same old m, okay, that you had already computed. Then you compute this v. Now you compare this v with respect to v1, v2, v3, whichever it comes closest to, right. If it comes closest to, let's say, 3, okay, in a simple kind of a norm sense, okay, v1 or whatever, right. So let's say v3 minus v. Okay, if this happens to be the smallest among all the, when you compare with all the means, then you would say that, right, he is that person. Now, right, this works very well. I mean, actually, right, it's not such a bad idea. It works very well if you give nice frontal faces. Okay, this struggles when there is the illumination variation. It struggles when there is a post variation, which is why, right, it never it never flew far, because they knew that there were some very, very fundamental constraints. You might say that, oh, why can't we take more images, ask this guy to look this way or that way, right, that side this way, and then take, but then people who will be willing to give you that many images, right. So illumination is again another issue. For example, shadows create problems, and also right, expression. Somebody may give a new expression later, and then right it'll. So it was not robust. It was good. I mean, if you kind of used a constrained atmosphere where you would right ask people to straight away look at the camera, don't give any expressions and so on, then it was okay. But then right those kind of things can't be used, right? So I thought wanted to copy something. Okay, let me see if I have it here, so that you will get an idea as to how these things look like. So if you see these faces, right? So these are some people, right? So whose images they've taken, right? Whatever, male, female, right? All of them put together, and then you construct something like an average face. This is what I said. This is your M. Okay, so this is like the average face, and then yeah, here are your eigenfaces. So eigenfaces, because you have mean subtracted them, right? So they look like a ghost face, right? So these are like, this is for example the top eigenface, then the next most significant, then the next most significant. So kind of ordered, okay, in some sense. In this case, I don't know, they've shown only first 10 eigenfaces. And then, okay, yeah, so the plot that I was mentioning, right, would be something like this, where you will be able to show where these guys are, right, after you do, I mean, after you find the features, you can reduce the dimension and then see how well separated they are and so on. Okay, so this, as I said, this was okay, I mean, as long as you were willing to work in a constrained atmosphere, constrained settings. Then I also wanted to show you, right, now another place, okay, where right, we had used it for was here. So right, until then people were using it for eigen. So this is face recognition. What I said is eigen face recognition. Now you can also ask, can I kind of locate human people? Okay, so human faces. So suppose I have an image, right, and suppose I have somebody there. Normally human faces don't, right, they occur very sparsely in an image, unless of course you're looking at a team, right, a cricket team or something, or a group photograph. Otherwise, normally when you look at an image, right, there'll be hardly like 2 or 3 people in an image, mostly one person, right, and then the idea is that can you use the PCA in order to be able to locate a face, right, where a human face is. You're not trying to recognize, just want to know where it is, right. So this is also very important, because this is in fact the first step, right, before you can do kind of a recognition, because you have to know where that face is, and then you can probably pass that on to this one recognizer, right. So in that sense, this typically is like a first step. So what I kind of said, so people what they kind of did was they kind of learned what is called a universal background, which is kind of difficult, I don't know, I could never accept that. It's like saying that whatever is not a face, right, is all background. Now what is not a face is like, all over the place, right. I mean, faces are that way very few. Okay, so there were groups that worked on that kind of problem, where they would have a basket of images which they would all classify as non-faces, and then they would have this basket where you have all faces, right, and again, right, and they would kind of use the idea that I know how a background image looks like, or a non-face looks like, and then I know how a face looks like, and then right, based upon that I'll try to do something. So what happens is, if you try to do something like that, right, then it hurts you, because of the fact that like I told you, I'll show the next one, okay, which will give you an idea about what will happen, right, if you try simply doing. Okay, I'm showing these just as additional applications of. Okay, I know that, right, we are kind of veering away from image transforms now, but that is okay, because you should not think that, right, this is the only thing it is used for. So for example, okay, this was a paper that when I sent, but this guy, right, did some very good work. So the idea was this. So if you try to use something like that, right, normally you will have like people, right, one or kind of 2 people in a scene, right. What will happen is, it will start to classify even other things as faces. But even if it puts, see, these multiple boxes you can remove. You can do what is called a non-maxima suppression remove. So you will get maybe 3 or 4 boxes. You don't need to see so many overlapping ones. But the idea is that even if you show one extra, right, it looks very jarring, because there is only one person. And then if you say there is that guy, and there's one more guy, and if you say that this is a human face, right, then you will wonder what the hell is this algorithm doing then, right? So you have to be very accurate. So especially when you localize faces, you can't afford to throw up something which is not a face and call it a face. So as I said, so learning kind of a universal background, right, did not at all appeal, at least to me. So what we did was, we learned a background with respect to that particular image. Okay, that seemed to make a lot more sense to me. Why should I worry about what the rest of the universe looks like, right? If I have this image and if I have to locate a face in that image, why not just simply worry about what is the background in that image and learn that? But if you do that, right, then what you have is something like an eigen background space, and then you have what is called an eigen face space. The face space is still the same thing. Whatever we did for face recognition, all those faces you can use to get an idea about how the eigen faces look like. But for eigen background, you have to pick patterns from this image from its own background. Now, which is actually tricky because you don't know where the face is, right? So, right, then what you can show is, okay, see, these eigen background images will look like that. Okay, this is with respect to some particular image. Okay, again it will change if you change the image. So it is like learning background on the fly. You change the image, you give me another image, then my eigen background will change. My faces will remain the same. I don't change my eigen faces, but my eigen background keeps changing, right? And therefore, now what you can do is, so if earlier if you had a result like this, then now you would have a result like that, where the box is exactly on where there is a person. So here, for example, it puts an additional box. Here there are plenty of boxes there, overlapping ones, of course. Again, here it's not even putting it correctly on this guy, whereas it comes bang on. And actually, right, in those days, people never talked about sparsity. The word sparsity was not actually used. Okay, in fact, right, that was the thing which was actually exploited. What was done was, in this case, right, it was simply a reconstruction error that we had to find out. And what we realized was, if you fix the basis images to be few, like for example, if you say that eigen background I'll only use 30, and similarly eigen faces also I'll use only so many 30, let's say. Then the idea was that if you had a face somewhere, then your ability to reconstruct face with eigen faces is far higher, is far superior than let's say when you use a few of these basis images. It's very, if you start increasing the number of eigenvectors that you start to use, right, then if you sort of throw away this notion of sparsity, then it becomes harder and harder. But if you say that, right, I'll only use a few of them, which is like sparsity, right? We never use the word sparsity. If you read that paper, never was the word sparsity used, but then later on people ended up showing exactly something similar. So the idea is that if you just use a few eigenvectors, then your ability to reconstruct that particular class is very high. So for example, if I use a background image, and if I try, because I do not know, right, whether it's a background or whether it's a face, so I kind of reconstruct it using my eigen background images, 30 of them. I also reconstructed using my eigen faces, again, let's say so many of them, 30 of them. Now, because it's a background, right, the eigen background can actually favorably reconstruct it much better than what the face can, because I'm using only so many. So if you throw in this kind of notion of sparsity and try to reconstruct, it will just show up. Okay, so earlier, right, if you had a problem, the problem was if you had only one sort of single metric, where you had only face and then you had an image, you didn't know whether it was a background or a face. For face you got a value. For let's say so for example, if you said that if it is closer than this value, I would declare it as a face, then what would happen is a face with a minor variation, it will end up having a slightly higher error, and then you would say it's not a face. Okay, so what will happen is either you end up declaring too many things as faces, even things that are not a face you declare, along with faces you declare them also as faces, which is wrong. Or if you right, make this very tight, then what will happen is you'll end up showing right, not even showing faces as faces. You will miss. Okay, so this kind of a threshold setting became a problem. Whereas with this kind of thing, what happens, you have this eigen background on this side sitting, the eigen faces sitting. Now you are not only computing one value, one sort of metric, you're also trying to find out what is it with respect to background. What happens is if this guy turns out to be a background, then its error with respect to background eigenface reconstruction is very small compared to with faces. So you have some notion of how well you are doing. Okay, that is what was used, and then we can even show it. I think I have even other examples. So even we took it here. Okay, this is all there, but even we came back here and took it right outside our building here, outside ESB. Right, so multiple people and all. Right, so it did pretty well. Okay, and of course we trained even for side faces and all. Okay, we didn't want to say restricted to. So even here, right, this is not frontal. This is in fact totally side. So all of that it could pick, and you see that, right, there are hardly any false pictures, false boxes, right.